chair of the first session, Chris Hull.
Thank you very much. It's a great pleasure to open the first scientific session. It's wonderful to be back in having a real-life conference after several years in the virtual wilderness. And our first speaker is Emil Martinec, who's going to reveal to us the brains behind black holes.
Okay, much better. Oh, maybe even too loud? Goodness. All right, so, hello? Okay, so my task is to review the fuzzball program. I thought I would begin by reviewing a bit the, let me just get my timer on. Review a bit black holes in general, and so what are we at? We've been striving for decades to understand the quantum mechanics of black holes and reconcile the seeming incompatibility of locality, causality, and unitarity in their quantum dynamics. And along the way, we probably want to understand the statistical mechanics that underlies the thermodynamics of black holes. And string theory gave us the first steps towards a resolution of that by accounting for the entropy of certain extremal supersymmetric black holes. In particular, the first one was the D1, D5 momentum three-charge black hole system, where the entropy is given by square root of the product of the charge quanta. And while that accounting is given in a weak coupling description, one's guaranteed by supersymmetry that the deformation to strong coupling preserves the counting of states. And so what was an interesting follow-on to this work was an observation of Strominger, Maldacen, and Horowitz that the full three-charge entropy, non-extremal, non-BPS, the supergravity solution could be thought of in terms of a bound state of the same brane charges, except allowing for both branes and anti-branes. And that suggested that even in the supergravity regime, in the gravity regime, that the black holes might be considered as some kind of composite bound states of the corresponding branes. And that then led somewhat later to the fuzzball idea proposed by Lunin and Matur, that black holes are indeed compact objects composed of the extended objects of string theory, but that have no horizons and therefore no information problem. And really, you know, this idea has sat around for the intervening 20 years, and it needs an understanding of the bulk side of the gauge gravity correspondence. And so one way of thinking about what's going on with this entropy formula is that each kind of brane in the bound state, its entropy is multiplicatively enhanced by the presence of the other branes. And we know simple examples of this. For instance, string winding fractionates momentum, that the momenta quanta are fractionated in units of 1 over the string winding. Similarly, 5 branes break fundamental strings, or whatever strings bind to them, into what are called little strings, whose string tension is a fraction of the fundamental string tension. And one can think of the symmetric orbifold that describes the entropy in a corner of the moduli space as the Fock space of little strings at weak coupling. So what we'd like to do is to tie this intersecting brane picture to some kind of bulk geometric picture. And what I'd like to explore is the particular duality frame where the strings are fundamental strings and the fibranes are NS fibranes. And the reason for doing that is that the NS fibranes are heavy. Their tension goes like 1 over the string coupling squared. And so they're really to be thought of as solitonic objects. And so if we can describe them using worldsheet dynamics of the fundamental strings, a lot of the back reaction will be incorporated in finding the appropriate semi-classical solutions. And furthermore, the worldsheet theory will keep track of various stringy properties of the background. Now, one thing I also need to do is to clarify some misconceptions which seem to have risen in recent years of what a fuzzball is. So there are various gradations of fuzzballs. The one that's been mostly explored are what are called microstate geometries, which are smooth, horizonless solutions of the supergravity field equations whose field gradients are small everywhere. And passing beyond that, one might consider some kind of perturbatively stringy microstates where, in a worldsheet construction of these horizonless solutions, we allow for string scale gradients of the background. And examples of the above, which we'll encounter later in the talk, are what are called supertubes, that is 2-charge BPS solutions, and adding the 3rd charge, making something called superstratum. Now, the generic fuzzball is the generic object which contains all 3 of the background charges and may or may not have a nice geometrical description in all parts of the spacetime. And one thing we know for sure is that the number of that the set of microstate geometries is contained within the set of perturbatively stringy backgrounds, is contained within the set of generic fuzzballs. I think we also know that the number of these is much, much smaller than the number of these, much, much smaller than the number of these, parametrically in the charges. Okay, so let's start with the 2-charge BPS states. The supertube geometry is some complicated looking mess, but basically all these BPS solutions have coefficients of metric coefficients and coefficients of the other fields, which are various harmonic forms or harmonic functions that are, in the case of the supertube, sourced along a contour by some set of source functions, Fi of v. And in particular, among those source functions are the source functions that say where are the 5 branes in their transfer space. So I've depicted 2 of the coordinates transversed to the 5 brane here. This direction is the coordinate y, and I think I should have said the compactification we're looking at is one where the 5 branes are wrapping both a T4 and an S1. The strings are wrapping in S1. I will parameterize this S1 that is wrapped by both branes by y. So when I talk about the y circle, I'm talking about that circle. Okay, so along the y circle, the strings and 5 branes are wiggling in some way. They give rise to this source contour, and the various source functions then determine, through a Green's function integral, the harmonic forms and functions that specify the background. Now, the half BPS bound states, we can think of this source contour set of functions as having some set of Fourier modes whose occupation numbers are Nik. And then the accounting of the different 2-charge microstates is just basically given by specifying how many excitations you have in the kth mode in the ith polarization. And the polarizations include the scalars that specify where the 5 branes are in their transfer space, some kind of internal gauge modes on the 5 brane, and their fermionic partners, in the case of T4. And one can understand this quite easily by thinking about T-duality of this background to NS5 momentum. T-duality along the Y circle, where this is just the Fock space of fractionated momentum modes on a single 5 brane that wraps the T-dual of the Y circle and 5 times. Okay? And so coherent states correspond to particular horizonless supertube geometries, and the typical state's highly quantum. And one way of qualitatively thinking about what's going on is that as you make the contour in the transverse space more and more compact, these functions become more and more peaked. In particular, the coefficient of dt squared is going to 0, so the redshift is getting larger and larger as the radius of gyration of the five-brane becomes smaller and smaller. Okay. Now, one thing that's nice about the NS frame is the ability to go beyond supergravity, because the background describes a nonlinear sigma model, which long ago, with this amount of symmetry, was shown to be exactly conformal to all orders in sigma model perturbation theory. And from what I'll be describing during this talk, we also have a good grip on the stringy, perturbatively stringy, non-perturbative structures. And that comes about because one very particular nice coherent state of the background, namely a background where only a single transverse scalar mode is excited in the kth oscillator mode, and then just populated as many times as we need to fill up the background charges. That particular background describes a supertube which is spiraling around in a particular transverse plane, described as the x1, x2 plane. Okay, and it turns out that worldsheet string theory in this particular background, sourced by this particular brane configuration, is exactly solvable on the worldsheet. What is it? Well, what is the geometry that's being sourced? It's something where asymptotically at large radius it has the linear dilaton throat of N5 five branes, but that at some radius, at some radial scale, determined by the scale of the size of the Y circle in the background, the geometry rolls over. If you like, the fundamental string sources begin to affect the background, and the geometry rolls over to an ADS3 cap with a ZK orbifold point at the tip. Okay? And the worldsheet theory that gives this background, I should say, that's of interest because in the limit Ry goes to infinity, which is the ADS3 limit, basically if you make the Y circle bigger and bigger, you increase the amount of the geometry that's in this ADS3 regime. And so the limit Ry goes to infinity is the limit where the entire radial geometry is ADS3. And in that limit, we can plot what we're looking at as in terms of a phase diagram of in the resulting dual conformal field theory. And the states we're describing are some sequence of geometries which, as we make K bigger and bigger, have a more and more compact source. This tip becomes more deeply redshifted and more cuspy, and one marches in systematically towards the extremal black hole limit from below. Okay, so and the worldsheet theory that describes this is a Gage-Wessomino-Witten model, where roughly speaking you can think of these factors as describing the directions along the five branes, and these directions as describing the directions transverse to the five branes. And you'll note that there are too many dimensions here. There are 12. And so we get rid of 2 of them by a gauging procedure. And the particular current we describe is this one here. The factor K that describes which one of these geometry we have is basically a discrete parameter that describes the embedding of the denominator group into the numerator group. Okay, and once having that, we can describe nearby supertubes by looking at the vertex operators in this worldsheet conformal field theory. Among those vertex operators are the half BPS vertex operators, and so half BPS vertex operators preserve all the supersymmetries that the background preserves, and therefore acting with those on the background gives you another nearby half BPS state. And so by studying the properties of those vertex operators, you can see what those vertex operators are doing. They basically take some number of fundamental string degrees of freedom that are bound to the five branes, extract some number of them, and make a transition to another a different winding, not the winding sector K, but the winding sector 2J plus 1K plus WYN5, where WY is some additional winding on the Y circle that's added by the vertex operator. And then, of course, you can also change the polarization state. The polarization state is determined by whether you're looking at a Navier-Schwarz vertex operator or a Ramon-Ramon vertex operator. Okay. And so perturbatively then, nearby, we can get, more generic states. Every time you act with a vertex operator, you're pulling out some number of these background strands and changing them to something else. And so in principle, you might say that by taking these vertex operators, which are just 1-1 operators on the worldsheet, and exponentiating them into the worldsheet action, you should be able to coherently deform to any nearby supertube background. Now, one interesting aspect of these vertex operators is that a piece of the Gage-Weston-Witten model is SL2R conformal field theory. And it's known that in the representation, affine SL2R representation theory, there's an identification of states in the theory where certain states at winding 0 are exactly equivalent to states at winding 1. And this feature feeds through into this Gage-Weston-Witten model into a statement that any of these half BPS vertex operators can be thought of either as just a point-like graviton vertex operator or some kind of string winding vertex operator. So the vertex operator perturbs both at the same time. It changes the fundamental string condensate that's bound to the 5 branes through this aspect of the vertex operator. At the same time, it deforms the geometry through the gravitational aspect of the vertex operator. Okay. And as we'll describe a little bit below, this winding string aspect is important for understanding what happens when the source gets very stringy. We'll see. All right. So a little bit more specifically, what do these graviton vertex operators look like? They're standard string vertex operators. They have some center of mass wave function describing some winding on the Y circle, some center of mass momenta, some center of mass wave functions in both SL2 and SU2, and then a pair of oscillator excitations describing which supergraviton you're talking about if you're in the NS-NS sector, and spin fields for the Ramond operators. And those to be half BPS, they need to be the condition. If you follow things through, the condition that such a vertex operator be a half BPS is that both on the left and the right moving current algebra structure, the states be highest weight in the center of mass. And so if we want to think about quarter BPS deformations are those which are going to add the third charge to the 3-charge system. So vertex operators that carry that third charge are ones that are, say, not half BPS, say, on the left moving structure. And we get that by relaxing this condition of highest weight structure. So quarter BPS vertex operators are things which we still want the same sort of graviton structure. But we allow something that's an excited state away from the highest weight state in the center of mass. And we can do that both in SU2 and in SL2. Now, what you're doing on the worldsheet is you're exciting the structure with zero mode excitations, either in SL2 or SU2. And in space-time, it turns out that, in the worldsheet theory of SL2, these global symmetries on the worldsheet translate to the global symmetries of the space-time CFT. So, in particular, this is L-1 in space-time, and this is J0 plus in space-time. And so one is indeed perturbing the background by things that add the corresponding momenta. And if you look carefully at the physical state constraints, one of them tells you that the sum of the deformations in SL2 and in SU2 add up to k times the y momentum. So what you see is that there's a family of excitations with some total momentum added perturbatively given by the properties of the background. And for T4 as part of the 5-brane world volume, one has a choice of 8 Nivard-Schwarz and 8 Ramon left polarizations and 2 and 2 on the right. And so there are sort of this many, I guess this is 16 times 4 is 64 different supergravitron polarizations, half of which are bosonic and half of which are fermionic. In addition, so if you look carefully, the half BPS vertex operators are allowed to have winding on the Y circle. The quarter BPS ones are allowed to have momentum on the Y circle. But if you ask that you have both at the same time, then level matching constraints on the world sheet force you to have some left-moving oscillator excitations. And so there are additional quarter BPS vertex operators, but they're intrinsically stringy. And if you do a very naive counting, there are going to be many more of these than there are of these. So these guys will map onto the quarter BPS microstate geometry solutions. These will be some kind of stringy extensions. And furthermore, neither of these is going to saturate the BTZ entropy. Okay. So. And why do I say that? Well, as I was saying before, the worldsheet gauge constraints tell you that the excitations of SL2 and SU2 tell you about the Y momentum, but notice that the Y momentum comes in fractions of 1 over K. And similarly, if we excite the oscillators with the stringy quarter BPS vertex operators, the oscillator excitations come in momenta quanta of 1 over the fundamental string winding. And neither of those is as big, neither of these fractions is as big as the fractionation of the total winding that the vertex operator creates. The vertex operator creates this total winding, and yet we don't seem to get that most finely graded momentum excitation. And so it seems as though the perturbatively stringy excitations do not contain the most finely graded momenta, which are responsible for the largest amount of entropy in the 3-charge bound state. And very likely, this is because one's working in a regime where the 5-brane has been pushed apart by the string condensate that it carries. And by being pushed apart, all the non-abelian excitations of the 5-brane have been Higgsed a little bit. And what you're doing when you decrease that radius of gyration to bring the 5-brane strands closer together is you're getting closer and closer to the regime of non-abelian 5-brane dynamics. How am I doing on time? Okay, good. So much for the linearized perturbations around some very specific, very symmetric round supertube. We might ask for these quarter BPS excitations, in particular these ones that are describing excitations that live within supergravity. What happens, so we know what happens when we condense these. We get this generic supertube, which is described by the Luhnen-Matur solution in terms of some wiggly profile functions. So we'd ask, okay, what happens when we condense these quarter BPS vertex operators? And the answer is a set of solutions called superstrata. So these are coherent coarse condensates of the quarter BPS supergravity perturbations. They're again, the geometries are described by some set of harmonic functions. After a good bit of work, it was noticed that one can solve the BPS field equations in a systematic hierarchy, where first one specifies some aspects of the transverse four-dimensional geometry, and then one solves for some set of harmonic functions, and then one solves for the momentum and angular momentum harmonic forms and functions. And all of this in some sort of staged hierarchies where at each stage you're solving linear equations, but the sources for those linear equations are quadratic in things you solved for previously. And what does the geometry look like? Well, in the interesting regime of parameter space, they basically look like ADS3 down to some radius that's controlled by the momentum that's carried by the geometry, where basically the momentum acts as a pressure which stabilizes the Y circle at some radius, and then one develops a long ADS2 throat, which is the stabilizing is happening because the geometry is carrying some explicit momentum wave, this superstratum mode, which perturbatively is this quarter BPS vertex operator I was talking about. And at that point, once you get sort of inside that momentum wave, the radial geometry starts shrinking again and caps off smoothly in something that's approximately global ADS3. So one can, again, label these quarter BPS vertex operators by the quantum numbers they carry. In symmetric product orbifold language, the states, the individual string modes, little string modes that are being excited look like this, some particular Ramon-Ramon mode, and then potentially excited with various global excitations. Recently, it was also noticed that, in addition, one can extend this to certain 60 vector multiplet deformations of the geometry, which I won't have time to describe. So, one question that a lot of people ask is, are these things black holes? Should they be counted among the black hole ensemble? I think the answer is, well, the answer I would give is that they are they're microstate geometries for sure. They're things that are smooth on the string scale. They're perfectly well described in the supergravity approximation. However, they're extremely atypical because one has excited some very particular modes very coherently, and they don't exhibit this fine scale fractionation of the momentum that one expects for the typical state. But that's okay, as far as I'm concerned. What they do is they're things that carry the same charges. They're in the same superselection sector as where the generic state in that superselection sector is a BTZ black hole. So they're things that get you within the vicinity of the black hole state space without themselves being black holes. And so the question for me is, what happens when you perturb these things sufficiently? You expect they'll scramble into the generic microstate, which is looking more and more like a BTZ black hole. And one would like to follow that evolution, if possible, as far as one can. And so, of course, the fuzzball paradigm posits that whatever the thing is scrambling into also fundamentally doesn't have a horizon. It might look to the effective supergravity theory like a horizon, but fundamentally there's something there at the horizon scale which is carrying the entropy. And so the questions that I'd like to pose for the rest of this talk are, how well do these superstrata solutions and other microstate geometries approximate black holes? And can we see hints of fuzzball structure emerging in the scrambling dynamics? Okay, before getting to that, one thing you'd like to do is to check, how these things stand up as far as our holographic expectations. And the sorts of things that have been computed are 3-point functions of BPS operators, where you take two of those operators to be heavy to make the heavy background in and out state, and then you probe it with some light supergravity operator. Those checks have been performed and agree completely with what happens in the symmetric product, and that's to be expected because the thing you're computing is highly BPS. But in the process of making the checks, you need to understand a lot of properties of the bulk boundary operator map, and sorting that out is a useful exercise. Now, then 4-point functions, they're not protected, and so they provide, when computed in these superstratum backgrounds, they basically provide you a prediction for what the CFT should be doing at strong coupling. And so, for instance, if you look at the 2-point function, so if you could look at this particular 4-point function, you can think about it as a 2-point function of some supergravity probe in the heavy background in and out states that create the superstratum. And so one can extract that by solving the wave equation by standard techniques. And for sufficiently simple superstrata, namely those that are just have a single mode excitation, there are lots of killing vectors. You can separate the wave equation and solve it, and find that this two-point function looks an awful lot like the quasi-normal mode spectrum of a BTZ black hole, and that's simply because, you know, the geometry that you're looking at looks an awful lot like BTZ until you get down here in the cap of the geometry. So a wave sort of disappearing into the ADS2 throat has an exponential decay, as you would expect for a quasi-normal ring down. But then eventually the probe hits the cap and then bounces off the cap and comes back out. And so there's an echo at some time, which is of order the central charge, and so that's not very encouraging. You know, it doesn't look very much like a black hole if you wait long enough. But that's the supergravity approximation, and if you ask the same question in string theory, the thing you're dropping in is a gravity mode. The gravity mode is secretly some particular mode of the string, and you should really ask what's happening to strings in this background. And the thing is that the deviation of the background has very small multiples that in the background that differ from those of the BTZ solution. And even very far up the ADS2 throat, that deviation gets amplified by the blue shift of whatever you're dropping into this from the top of the throat. And so the tidal forces can get to be of order the string scale or larger. It's sort of the geometric mean of these two scales. So there's this scale where the cap is, there's this scale where ADS2 starts, and the geometric mean of those two scales is roughly speaking where the tidal forces get to be string scale. And so what you find is that if you then analyze the worldsheet dynamics of a string that's falling into this geometry, the tidal forces get big here. And by the time the string gets to the bottom of the throat, what's happened is that its kinetic a large fraction of its kinetic energy has been converted into stretching energy. One of the tidal forces is a stretching in some particular direction. And so that stretching just rips the string apart, makes it a big excited string by the time it gets to the cap, and now it's trapped because it doesn't have enough kinetic energy to climb back up. And so, you know, the idea is that a string falling in from the top of the throat gets tidally trapped and eventually settles down into the bottom of the throat and thermalizes. So that looks a little bit more like what a black hole would look like, except probably the time scales are wrong. What's going on is that the scrambling is the scrambling of the oscillator modes on a highly excited string, and not something associated to chaos near the horizon. Another thing you can look at, instead of looking at these probes dropped in from the top, the probes dropped in from the top are sort of like dropping a bomb into the bottom of this cap geometry. You could just say, okay, let me delicately place something in the cap of the geometry and ask what happens to it. And so there, again, because the radial wave equation is separable, since the wave equation is separable, you have an effective problem for the radial dynamics, which consists of some kind of metastable bound state for the modes that are bound to the cap. And those have some probability of tunneling through the ADS2 throat out to the asymptotically flat region. And so this is sort of the superstratum version of Hawking radiation, that there are things that are thermalized in the cap, and over some time scale, they tunnel out to asymptotically flat space, radiating away at some rate. Okay. So you could ask, okay, how many of these superstratum modes are there? I said there were many fewer than the BTZ entropy, and here's the precise number. The BTZ entropy is square root of n5, n1, np. The very naive accounting of how many of these things there are. Well, not naive. A very careful accounting of how many of these things there are based on constructions that were known at this time, estimated some number of order square root of n5, n1, np to the 1/4. And so, as I was saying, parametrically in the charges, there are many too few of these smooth microstate geometries. However, one thing one does know is that in the perturbative limit, where the number of excitations away from the round supertube is order 1, each of these deformations that accounts for this entropy matches a particular quarter BPS supergravity vertex operator among the list that I described to you before. And the ones of the initial constructions of these microstate geometries account for, roughly speaking, about half of these. The vector mode deformations that I mentioned earlier describe quite a few more. They may, in fact, saturate everything that one can do. But basically speaking, of the microstate geometries which have been enumerated already, there may be, half again as many, but basically they've all been accounted for. And so this, I think, one expects to be about all there is in terms of smooth geometries. Okay. One thing that's been happening recently is that the beginnings of the exploration of non-BPS perturbations around these cap geometries. And so one does that by making some particular ansatz and then truncating things to the full 6-dimensional dynamics to some kind of ADS3 dynamics. And then the set of equations you need to solve are some 11 functions of one variable that all talk to each other, so it's hugely messy. But using various numerical and perturbative techniques, one has begun to get a handle on these solutions. And one thing that's seen is that the non-BPS deformations lead to a feature you begin to expect in some kind of, scrambling dynamics, that the frequencies of the oscillations in the cap depend non-linearly on their amplitudes, as you would expect once you lose the BPS property. Okay. So I've described for you the smooth solutions, and I said, well, we have this worldsheet theory, and if it's good for something, it should be good for telling you what's going on beyond the supergravity approximation, when things start to become stringy. And as I was saying, the solutions are nice and smooth because what you've done is you've separated the 5 brane sources and abelianized the dynamics. And so what we'd like to do is to see, what happens when we start, getting 5 branes coming close to one another. And what we do see indeed is, what look like the W strings of little string theory. And I'll describe that in a minute. Okay. And I should emphasize that we're seeing all of this, this is going on way deep down in, already we've taken some decoupling limit. We're in, deep in some ADS3 region, and we're seeing structures in the bulk that, mimic what you would expect to see when a black hole is starting to form. Okay. So we're not just making some vague statements about, there's some Hawking-Page phase transition going on. So remember what the structure of these half BPS solutions is. There's some wiggly 5 branes, and a part of that structure is that along this contour is sourced a Kaluza-Klein dipole charge. And so there's some this contour is in part the core of a Kaluza-Klein monopole. And so when the 5 branes come close to touching, the Kaluza-Klein monopole cores come close to touching. And so there's a minimum size S2 for any pair of such nearly coincident 5 branes. Okay, and we're in type 2b, so we can wrap a D3 brane around that minimum size S2, and that leaves one leg of the D3 brane left over. It's trapped to wander along the T4 because this is a 5 brane structure, and so it has to be along where the 5 branes are. And so what you get is an effective W string. This is, if you like, the natural W brane object of type 2b little string theory. And of course, when the 5 branes actually self-intersect, that D3 brane becomes massless or tensionless. And so this is a tensionless string limit where string perturbation theory is going to break down. And it's my expectation that this is where the bulk of the entropy is hiding. This is where you start restoring the non-abelian brane dynamics, where you start expecting to see the Hawking-Page phase transition, but you're seeing it in the bulk dynamics. One thing that one can do is explicitly analyze one very particular symmetric deformation of this round supertube, namely deforming it into an ellipse. And so we did that a little while ago, and one can see indeed that the D branes that stretch across the ellipse along the semi-minor axis get lighter and lighter, and in the limit where the ellipse degenerates completely, those D branes become massless. On the other hand, just this past week, the corresponding superstratum, adding the third charge, was analyzed. And what one sees is that the geometry in the superstratum, as opposed to the supertube, develops a long ADS2 throat. So one is really seeing the non-abelian dynamics appearing at the same time that the ADS2 throat is becoming infinitely long. There's a dual perspective. Do I have time to describe it? Maybe. So let me just say quickly, okay, I do have time. These nonlinear sigma models have in them SL2R mod U1, and it's well known that there's a duality between this geometry and n equals 2 Liouville theory that has a vast extension in these supertube geometries, where if the supertube is only excited in one two-dimensional plane, there's a kind of a dual Landau-Ginzburg description of the sigma model. For those that know about such things, the structure of the superpotential is entirely coded by this profile function that specifies the Luna-Matur geometry. And what one sees is that when the 5 brane strands want to cross one another is precisely where two zeros of the superpotential coincide, the superpotential degenerates, and you see a rather standard singular limit of Liouville theory. All right. Let me use just a few of the minutes of the question period to describe something which I'm particularly enamored of, which is testing this thesis that it's little string dynamics that's responsible for the black hole entropy, and that is to get rid of the little string dynamics by getting rid of the T4. Remember, this wiggly tensionless string was wiggling in the T4. So if we get rid of the T4, we should get rid of the available Hagedorn entropy of the little string. And you say, well, how can I get rid of the T4? Well, perturbative string theory has no problem with that. It just means you have a non-critical string theory. It turns out you need to flatten the S3 a little bit to make that work. But what you find is that you indeed get a non-critical non-critical string theory which has no black holes in its spectrum. There are fundamentally no horizons, and so this thing doesn't exist. All you have at high energies in some thermofield double is an entangled string gas. So this is a situation where, because of the geometry, and I should say, when in the process the ADS3 becomes highly stringy. The curvature scale of the ADS becomes string scalar smaller. And so this is a situation where, in a highly curved geometry, no matter how highly excited the system is, it never forms a horizon, and the entangled string gas never makes a wormhole. So these models lie below a correspondence transition. Above the transition, you have geometry and BTZ black holes. Below it, you just have a gas of strings. And we identified what the dual CFT is. It's again a symmetric product deformed by the twist interaction that implements string interactions. But now the thing in the symmetric product is the space that's transverse to the little strings instead of the space that's along the 5 branes. And so it will be very interesting if we can manage to understand what happens to the high energy spectrum. We expect them to be Hagedorn fundamental strings instead of Hagedorn little strings. And the question is, how closely do they approximate black hole dynamics? Because there's a limit of these models where one goes to the correspondence transition. And so one should be more and more closely approximating in this system the dynamics of black holes. They have some features similar to the matrix model. I've run out of time, so let me just throw up my summary slide, and thank you for your attention.
Okay, thank you very much for a beautiful and comprehensive review. Questions? Yes. Okay.
So you described the story for ADS3 BTZ-like black holes. In the last few years, we've started to understand much better black holes that are intrinsically ADS4 or ADS5. There's a similar extremization principle as you began your talk with, but the extremization principle is qualitatively different. The extremization principle for computing entropy is qualitatively different from the way you motivate it for the F1P and S5 system. I was wondering what the prospects are for trying to understand microstates of these black holes.
Yeah, well, the analog of the half-peak distance, of course, were understood by Lin, Lunin, and Maldacena a long time ago. As far as I'm aware, there's less understanding once you start removing more and more supersymmetry. But I think it's something that's overdue for a revisiting, yes.
Other questions? Yes?
I was just wondering the timescales that didn't quite match you got much longer than the echo time for the string getting excited down the throat and, settling down. How much short does it fall off from what you would have expected for the genuine sort of Hawking evaporation?
So the echo time scale is associated with just the transit time between the top of the ADS2 throat and the bottom of the ADS2 throat. So one makes that longer and longer by holding the momentum charge fixed and decreasing the angular momentum. And so you can make it as large as of order 1 over n. But at that point, one is really losing control of the geometry because the cap is sort of order h bar above BTZ, and the fluctuations start getting large. So in the regime where it's trustable, I would say you're sort of away from the appropriate timescales one expects for BTZ. But anyway, I don't regard this as being something where you should say, oh, we're modeling black holes by this calculation. Rather, I would say that my takeaway is that the supergravity approximation to these very energetic probes breaks down, and so we should do something intrinsically more stringy. And so there are two more stringy things that happen. One is the thing I described, that the probe becomes a string and gets trapped. So that's already starting to, there is no strong echo in string theory. Everything just gets trapped and thermalizes, okay? And then you should ask, okay, how does it thermalize? Once the stuff gets trapped and I've got some energy in the cap, what does it do? Well, I think the first thing it should do is start moving me along the space of all these superstrata are built on top of some supertube base. And so once you have a little bit of energy, it costs you no energy because it's half BPS. You're on the BPS bound of the supertubes. It costs you no energy to start wandering around the phase space of supertubes. And so you'll start slowly wandering around the phase space of supertubes until you encounter the corners of the supertube configuration space where the phi branes start touching. And then you get non-abelian dynamics. So that would be my sort of low energy expectation about how the thing starts to scramble into something that looks like a black hole.
Yep.
Nice thought. Do you expect these the states that are not described naively by geometry to be some kind of geometry? Like, could they be singular geometry, or maybe they're not even given by metric? What is your expectation?
So in the two-charge geometries, it really looks like they become singular. It's you have some local ALE singularity that's wrapped by the D3 brane to make a tensionless string. And what's happening, you can check that all of the, usually when you have an ALE singularity, there's maybe some B-flux through the vanishing cycles that help puff things up. That all goes away when these things really collide. So it really is an ALE with no B-flux, and so you expect to be in some kind of singular, extremal black hole type geometry. What's seen in the three-charge examples where you go through exactly the same limit but adding the third charge, what you just see is an ADS2 throat that's getting longer and longer until you stop being able to follow it in the supergravity approximation. So it seems like there are these two things that are dual. You don't add the third charge, you see some geometry with singularity and tensionless strings. You add the third charge and you see an ADS2 throat that's getting longer and longer, and in the limit just becomes an ADS2 horizon. So somewhere in between those two, I expect one would hope to find, vestiges of the fuzzball. How can we bridge the difference between when we don't add the third charge, we definitely see tensionless strings. When we do add the third charge, we just see an ADS2 horizon.
Julian?
Hi, so you showed this, you showed this idea of calculating the spectrum of the stuff that tunnels out. How is it obvious that will be approximately thermal at the Hawking temperature?
Sorry, I missed because of the dings.
Oh, sorry. So you showed this picture of the radial effective potential of the thermalized strings that are trapped in the cap that can tunnel out. How is it obvious that will be approximately a thermal spectrum at the right temperature?
That depends on what you put in the cap. So, what's being done is just computing the linearized wave dynamics in a superstratum solution. And so you might say, well, maybe I have some something that might approximate a black hole if I put a thermal gas of gravitons in this ADS2 cap. It will be some thermal gas that's highly redshifted, and it'll radiate out at some weight. I don't know that's been computed. And moreover, once you start putting enough energy in the cap, then this scrambling dynamics, this thing I said before, that it's all being done with no back reaction. And I expect there to be back reaction because there are massless deformations that take you along this superstratum, this supertube dynamics that you don't expect the thing to sit there and be a fixed superstratum with a gas in it. It'll start wandering around and trying to find the parts of the phase space that have more entropy.
But is that calculation doable, or do you think it's just too ambitious?
I don't know if it's doable or not. I can tell you it hasn't been done. So analysis awaits us. But,
any more questions? Okay, I have a question. So the worldsheet picture played a very useful role here. Is there anything you can say about, say, the other dual versions, for example, the D1, D5 system?
Yeah, I don't know. I mean, I'm making very heavy use of, so I should say, the D1, D5 and the F1, NS5 picture are sort of valid and complementary parts of the moduli space. In the D1, D5 system, one thinks of having roughly comparable one brane and five brane charges. And if that's the case, then the D1, D5 is the appropriate supergravity, effective supergravity theory over the bulk of the moduli space. If, on the other hand, if you have NS5 branes, the only way that the fundamental strings are competing with something whose tension is 1 over G string squared is by having of order 1 over G string squared fundamental strings. Windings. Okay, and so it's in a vastly different, so the sort of the numbers of brane quanta are vastly different in that situation. And so it's not obvious to me that lessons one's taking from here go over directly to what's going on in the D1, D5 frame. So I very purposely went to some corner of moduli space where the world sheet string theory applies, and I'm not sure what to say about D1, D5.
Okay, thank you. Any more questions? If not, let's thank Emil again.